Okay, now that we've talked about effectively um, designing finite automata, or rather constructing finite automata that prove the closure operations for um, basic operations such as the complement, the union, the intersection, concatenation, and the star operation. I'd like to, before we wrap up Unit 7 and the closure properties, I would like to wrap up with and discuss about concatenate and creating other or rather proving other closures under other operations. One of the things that I would show here, there are many other operations that you can actually use this same method to go ahead and do the proof for, and I'm going to show and prove that the class of regular languages is closed under the relative complement. So what I would like to discuss here then is effectively to prove that the class of regular languages is closed under the relative complement. What that means is that if a sub 1 and a sub 2 are regular, then I would like to prove that a sub 1 minus a sub 2 is regular. So the proof here is actually not by construction, but I'm going to actually take a different approach. I know that a sub 1 is regular. Therefore, a sub 1 is a set. And there exists a DFA, or rather yes, a DFA actually. D sub 1 such that L of D sub 1 is a sub 1. A sub 2 is regular. Therefore, a sub 2 is a set. And there exists a DFA D sub 2 such that L of D sub 2 is a sub 2. Now, I would like to prove that a sub 1 minus a sub 2 is also regular. This is what I want to prove, and I don't know if it is the case. So I would start writing a sub 1 minus a sub 2, and then from the axioms of set, I know that a sub 1 minus a sub 2 is equal to a sub 1 intersection with the complement of a sub 2. Okay, so this is item number 1. I know that if a sub 2 is regular, then a sub 2 complement is regular. I know that, so let's call this number 2. I know that if some, let's say, B and C are regular, then their intersection is regular. Okay, so I have 3 items. So from 1, actually, from 1, I know that a sub 1 minus a sub 2 is effectively the intersection of a sub 1 and the complement of a sub 2. from 2, I know that if A sub 2 is regular, so will be its complement. And by combining these two from number 3, I get that A sub 1 intersects with the complement of A sub 2. So this is regular, will be regular. And then going back from item number 1, then A sub 1 minus A sub 2 is going to be regular. And that's completes my proof. So that's one way that I would talk about, or rather based on the proof theorems that we already have for the closure under complement, concatenation, star, union, and intersection, we can prove more complex operations. In this case, I proved that the class of regular languages is closed under the relative complement, in that if A sub 1 minus A sub 2 is, if A sub 1 is regular and A sub 2 is regular, then the set built by subtracting A sub 2 from A sub 1 will be also regular. So this is the proof. Now, how would the construction work then? So if I'm asked to, so if I'm given, so if you have dfad sub 1 and dfad sub 2, how would you construct D such that L of D is equal to A sub 1 minus A sub 2? How would we do this? So it's going to actually take 3 steps. Step number 1, build D sub 1, which we already have, and D sub 2, which we already have. Step number 2, from D sub 2, build D sub 3 such that L of D sub 3 is going to be equal to the negation or the complement of L sub 2. And step number 3 is from D sub 1 and D sub 3 construct D such that L of D then will be A my intersection with, or rather A sub 1 intersection with the complement of A sub 2. And this is how we're going to create, or rather construct, a machine based on the 2 machines for the 2 languages to calculate the, or rather to accept and recognize the subtraction of those 2 languages. Okay, so let's see an example. Let's say that we have 2 regular languages, and that let's say two deterministic finite automaton. Let's say deterministic finite automaton M, or rather, what did I call it? D sub 1 that accepts the okay. So let's say that I have this deterministic finite automaton D sub 1, and then it's made of these states Q0, Q1, Q2, and Q3. And basically what this machine does is that it accepts a language that in which all strings start with 2 consecutive 1s. Okay, so D sub 1 is this finite automaton. So L of D sub 1 is language A sub 1, is the set of all the strings where W starts with 1 1. Okay, so that's one of the languages. And so then I have another automaton, and let's say that this automaton represents a language in which all strings end with 0. And in this case, then what I would have is going to be an automaton d sub 2, and this will have two states. And I'm going to call these states R. So I'm going to have an R sub 0 and R sub 1. So R sub 0 is the state in which I'm not, it's a string that doesn't end with a 0. When you see a 0, you go to R sub 1. You stay in R sub 1 for as long as you see a 0, and then you go back to R sub 0 when the moment you encounter 1. So effectively, the second automaton down here, its language is the strings that all end with zeros. The last element in this language is going to be in the strings of d sub 2. It's going to be basically 0. Okay. So then the language of d sub 2 is a sub 2, the set of all the strings such that string ends in 0. Okay. Now, how about if I wanted to make a finite automaton of these two languages? So I want to construct D such that language of D is a sub 1 minus a sub 2. Or in other words, if the string starts with two ones, it must not end with a 0, right? So it's going to be the set of all these W's such that W starts with 1 1 but doesn't end in 0. Okay, so effectively that set is the equivalent of the subtraction of these two sets, or the relative complement of the set a sub 1 minus a sub 2. So the proof is going to be, again, a 3-step. So we already have d sub 1, we already have d sub 2. Based on d sub 2, we construct the machine that recognizes the complement of d sub 2, and then based on our construction mechanism for the intersection, we build a machine that recognizes the intersection of a sub 1 and a sub 2 complement. So from d sub 2, we know that, so first is construct a DFA that recognizes complement of a sub 2. So the method was just change accept and non-accept states of d sub 2, right? So then d sub 3 will become, well, actually let's write these guys down then. So in d sub 1 is effectively q sub 1 sigma delta sub 1 q sub 0 and the set q sub 2. And d sub 2 is, let's call this r, sigma delta sub 2 r sub 0 and r sub 1. Now from here, d sub 3, actually from here up here, then d sub 3 will become, you keep the states, you keep the sigmas, you keep the delta transitions, so it's delta sub 2, then you keep the start state, and now the accept state will be the set of accept states of d sub 3 is the non-accept states of d sub 2, and the set of non-accept states of d sub 3 will be the set of accept states of d sub 2. So all we need to do is just to flip these sets. Okay, just to point out here, in Q sub 3, we also go back to Q sub 3 for both zeros and ones. Now the next step is construct D based on, or rather let's call this D sub 4, based on D sub 1 and D sub 3. Okay, so how are we going to do that? This construction is basically with the cross product. Remember the cross product method that we said? So D sub 4 is going to be a 5-tuple. Let's call this Q sub 4 and sigma and delta sub 4, and the set Q sub 4 0 and the accept state F sub 4. And I'm going to build all of these components for my machine. Okay, so since I want D sub 4, I want L of D sub 4 here basically, which is the same thing that I earlier called D, is going to be A sub 1 intersect A sub 2 complement. Since this is an intersects, then I would like to simulate both D sub 1 and D sub 3. So I use the cross products. So from here, then Q sub 4 is going to be the cross product of Q and R. So it's going to be Q sub 0, R sub 0, Q sub 0, R sub 1, Q sub 1, R sub 0, Q sub 1, R sub 1, Q sub 2, R sub 0, Q sub 2, R sub 1, and finally Q sub 3, R sub 0, and Q sub 3, R sub 1. So that's the set of my my constructed machine. The sigma is the same for all three. So it's going to be the set 0 and 1. The set of my accept states Q sub 4 0 is going to be the pair in which both are or rather start state would be the pair of both start states. So it's going to be Q sub 0 and R sub 0 for both of the machines. And then the accept states here, since I want the F sub 4 to be the set of pairs in which both states are accept states, so it's going to be the cross product of F sub 1 cross F sub 3. So F sub 3 basically is that guy. Just draw this with a different color. So this is F sub 3, the set of accept states that accepts the complement, and Q sub 2 is the F sub 1, the accept states of the first guy. So this is going to be the set Q sub 2, comma R sub 0. So this is going to be the set of my accept states of the machine that recognizes both A sub 1 intersect A sub 2 complement. And now finally, I have to come up with my delta transitions. So the delta transitions then, in this case, let's actually draw the delta transitions here. So delta sub 4 is what? How can we compute delta sub 4? So delta sub 4 is from the Q sub 4 cross sigma over to Q sub 4. In other words, delta sub 4 for every Q from the set Q and R from the set R and A from your sigma alphabet, then the delta sub 4 takes in the form of getting two states, Q and R, and the alphabet A, and then producing a pair of two states. The first one from the delta sub 1 of Q and A, and the second one from the delta sub 3 of Q and A, actually R and A, right? So, so this way we're constructing the computations, the computation of our machine. So then let's write these down. So we have 8 possible pairs of states and 2 possible inputs, 0 or 1, and then we're going to compute the set of these states. So the way that then that calculation will go is, will be effectively 8 possibility for our states. So we would have Q sub 0, R sub 0. I'm going to just, yeah, let me write these with ordered pairs too. Q sub 1, Q sub 2, Q sub 1, Q sub 1, Q sub 2, Q sub 2, Q sub 3, Q sub 3. And for each Q sub 1, there's going to be either R0, R1. And for Q sub 2, it's going to be R0, R1. And for Q sub 3, it's going to be R0, R1 for the second pair. And so this is delta. And then the delta will be from 0 or 1. And of course, these are going to be pairs. I'm going to write them all down. Okay, and so Q sub 0 over 0 goes to Q sub 3. So this 2 go to Q sub 3, Q sub 3. And then Q sub 0 over with 1 goes to Q sub 1. So these 2 go to Q sub 1, Q sub 1. Q sub 1 with 0 goes to Q sub 3. So these guys go to Q sub 3 as well. And then Q sub 1 with 1 goes to Q sub 2. So these guys go to Q sub 2, Q sub 2. Q sub 2 with 0 and 1 stays in Q sub 2. So these guys stay in Q sub 2. Q sub 2 and Q sub 2. And then Q sub 3 for 0 and 1 both stays in Q sub 3. So these guys are going to stay in Q sub 3 for both 0 and 1. And these guys are going to go stay in Q sub 3 as well. So that does the first machine. Then for the second machine, let's put the commas here, comma, 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 comma. Then let me just be a bit more clear. This is Q sub 2, Q sub 2, Q sub 2, Q sub 2, and Q sub 3. Okay, now let's go and do the R states. So R sub 0 with 0 stays in R, with 0 goes to R sub 1. So R sub 0 with 0 goes to R sub 1. R sub 0 with 0 goes to R sub 1. R sub 0 with 0 goes to R sub 1. R sub 0 with 0 goes to R sub 1. Okay, R sub 0 with 0. Then R sub 0 with 1 stays in R sub 0. So these guys stay in R sub 0, R sub 0, R sub 0, and R sub 0. R sub 1 stays with R sub 1 at 0. So these guys stay at R sub 1. This guy stays at R sub 1. This guy stays at R sub 1. This guy stays at R sub 1. And then R sub 1 goes to R sub 0 with 1. So this is going to go to R sub 0, R sub 0, R sub 0, and R sub 0. Let me clean these up a little bit also. So that's one pair there, one pair there, and one pair there. Okay, and so finally, the way that this machine would look like, and so this is going to be my start state, Q sub 0 and R sub 0, and Q sub 2 R sub 0 is going to be this. This is going to be my accept state. So I'm going to just put 2 stars next to it. So then, how does this machine would look like? So let's draw its state diagram. So we start with the start state. So start state is Q sub 0 R sub 0. Then Q sub 0 R sub 0 with a 0 goes to Q sub 3 R sub 1. So with a 0, Q sub 3 R sub 1, Q sub 3 R sub 1 with a 0. And then with a 1, it's going to go to Q sub 1 R sub 0. Okay, so now that I did that, let me just draw a little line through it so that I kind of sort of know that I've done this. Okay, so this is done. Actually, you know what? Let's put a little check mark next to the states that are done. Okay, then let's go to Q sub 1 R sub 0. Q sub 1 R sub 0. So now we're going to do this state. Q sub 1 R sub 0 with a 0 goes to Q sub 3 R sub 1. We already have it up here. So with a 0, it's going to go there. And then with a 1, it's going to go to Q sub 2 R sub 0. So Q sub 1 R sub 0 with a 1 goes to Q sub 2 R. So with a 1, we're going to go to Q sub 2 R sub 0. And of course, Q sub 2 R sub 0, if you notice here, it's an accept state. So let's draw another circle through it to denote that that is an accept state. Okay, so now Q sub 1 R sub 0, I have both 0 and 1 transitions for it, so that is done. Next, let's go to Q sub 3 R sub 1. Q sub 3 R sub 1 is the last one here. So with a 0, it's going to stay in itself. And with a 1, it's going to go to Q sub 3 R sub 0. So then with a 1 transition, we're going to transition into Q sub 3 R sub 0. Then, so that's done. Then let's go to Q sub 2 R sub 0, this state, and see what its transitions do. So with a 1, we're going to stay here. And with a 0, we're going to transition to Q sub 2 R sub 1. With a 0, it's going to transition into Q sub 2 R sub 1. Okay, then let's do the transition of Q sub 2 R sub 1 as well. Q sub 2 R sub 1 with 0 stays in itself. And with a 1, it's going to transition back to Q sub 2 R sub 0. So then, let me just draw this back with a 1, we're going to transition back here, then with a 0, we can transition this way. Okay, and Q sub 3 R sub 0, with a 0, it's going to transition back into Q sub 3 R sub 1, and with a 1, it's going to stay where it was. Then I'm going to redraw this transition, kind of make it a little curved arrow. Okay, so this is it actually. If you look at this state machine, for every state that is reachable from the start state, we have a 0 and a 1, 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 and a 0 and a 1 transition. And if you notice, these states are not reached. So if you look at, for example, this state here, Q sub 0 R sub 1 was not reachable from the start state. So if you want to think about it, this Q sub 0 R sub 1 would be a state down here that would transition into these two states, but it was not reachable. And same with Q sub 1 R sub 1. So Q sub 1 R sub 1 would transition between, so Q sub 1 R sub 1 would be a state that would transition between these two states, but it's not reachable from the start states. So if we want to simplify our machines, we can get rid of these. So these states are not reachable from your start state, which is Q sub 0 R sub 0. And therefore we can remove these states. So we can basically get rid of these states altogether, and also the state we can get rid of. So this will be my machine that recognizes the relative complements of A sub 1 or A sub 2, which is effectively the intersection of A sub 1 with the complement of A sub 2. So as you see, if you are given a regular language that may be designed by subtracting two languages, intersecting, complementing, or even unioning, and all these different kinds of combinations of operations, you could build a machine based on whatever construction that we have done so far that would recognize your end result language. So with this, I think our Unit 7, the proof of the closure properties of the regular operations on regular languages is completed. And from this point on, we have all the tools in the toolbox that we need to proceed to start defining regular expressions, and then see what regular expressions are and prove the equivalence of regular expressions in regular languages. And then from that point on, we can actually look at the limitations of regular languages and finite automata and come up with a mathematical way to prove that certain languages are not regular. And that would gives us a good segue to the next phase of this class, which would be designing context-free grammars and context-free languages. Well, I hope that you enjoyed this unit and that you are also enjoying this class so far. And let me know if you have any questions in the discussion boards. Try to finish up your third homework assignment before we get to the other areas in this class. Thank you very much, and I will talk to you in the next unit.